Hello viewers, I hope you are all doing well. Welcome back to ECEA. Today we are starting our chapter number 24 named Economic and Product Design Considerations. Economic and Product Design Consideration in Machining. There are four basic things. First is machinability, second is tolerances and surface finishing, selection of cutting conditions, and product design consideration in machining. First of all, we will discuss machinability in some aspects. A relative ease with which a material, usually a metal, basically we are dealing with the metals, can be machined using appropriate tooling and cutting conditions. It depends not only on work material, but actually the types of machining operation, tooling, and cutting conditions are also important factors. Machinability is basically the thing that how we can apply the machining operations on some tools, some metal materials basically. Machinability criteria in production. There are different criteria. First of all, tool life, that how long the tool lasts for a given work material. Forces and power. Greater forces and power mean lower machinability. If there is greater forces and power, means the time is more required for machinability. It has low machinability. Surface finish. Better finish mean better machinability. For the better surface finish, more machinability, more machining is required. Ease of chip disposal. Easier chip disposal mean better machinability. These are some criteria for the machinability in production. Machinability testing includes most tests involve comparison of work material. Performance of a test material is measured relative to a base material. That there is some standard material, some base material. Relative performance is expressed as machinability rating, MR. MR of the base material is 1, that is 100%. MR of test material, for which we are going to test the machinability rating, is greater than 1 or 100%, means better machinability. Sorry. Machinability tests include tool life, it is the most common test. Tool wear, that how much time is a tool is taken for a wear. Cutting forces, that if there is more force required, the machinability is high. Power required in operation. Cutting temperature, if the temperature is rising suddenly, then it's mean that machinability is high. Material removal rate under standard condition. If less material is removing under the standard condition, it's mean it has high machinability. Mechanical properties that affect machinability. Number one is hardness. High hardness means abrasive wear increases to tool life is reduced. So the tool life is reduced because the hardness is high. Strength. High strength means cutting forces, specific energy, and cutting temperature increases. Ductility. High ductility means tearing of metal as a chip is formed, causing chip disposal problems and poor surface finish. Tolerances and surface finish in machining. Tolerances. First of all, we discuss tolerances. Machining provides high accuracy relative to most other shape making process. Closer tolerance usually means higher cost. If we move closer toward the tolerances, it means we required more machining and required higher cost. Surface roughness is machining is determined by geometric factor of operation, work material factors, and vibration and machine tool factors. These are some factors that cause the surface roughness. There are some geometric factors that also affect the machining parameters. Machining parameters that determine surface geometry includes type of machining operation, that if we are doing milling or the turning. Cutting tool geometry, especially the nose radius, and finally the feed. These are the surface geometry that would result from only these factors, that is equal to ideal or theoretical surface roughness. Now we will move toward that how the nose radius affects. If we have larger nose radius, it is near to the smoothness. If we have zero nose radius, it is sharper edges. These are the serrated like structure. So it is not the good cases. The effect of feed is that if we move towards small feed, we get good things. If we move to a large feed, it is not the good idea for the surface finish. Effect of end cutting edge angle is in if we have less angle, we have more smoothness. If we have large angle, it is not a good case in this. Now, ideal surface roughness is given by Ri is equal to feed square f square divided by 32 nose radius, 32 times nose radius. Work material factors includes built-up edges effects, damage to surface caused by chips, tearing of surface when machining ductile material, and cracks in surface when machining brittle material. Friction between tool flank and new work surface. Effect of work material is given in the chart. Ratio is given this side and this is cutting speed. As the cutting speed increases, ratio is decreasing, and this is the curves of different metals. This is ductile, this is cast iron, and this is machining, free machining alloys. To predict actual surface roughness, first compute ideal surface roughness value and then multiply it by the ratio of actual to ideal roughness for the appropriate class of material. In this way, we can predict actual surface roughness. Vibration is also known as chattering. Related to machine tool, tooling and setup, chatter in machine tool or cutting tool, deflection of fixtures, and backlash in feed mechanism is the basic cause of vibration. If chatter can be eliminated, then surface roughness is determined by geometric and work material factors. How to avoid chatters or vibration? Add stiffness or damping to the setup. Operate at speed that avoids cyclical forces that correspond with the frequencies, natural frequencies. Like we have the objective of this point is to reduce the resonance, reduce feeds and depth of cuts, change the cutter design to reduce forces, use a cutting fluid. Selection of cutting conditions. One of the tasks in process planning for each operation decision must be made about machine tools, and cutting conditions. These decisions must be given due to consideration because the work part machinability, part geometry, surface finish, and so forth. Cutting conditions, speed, feed, depth of cut, and cutting fluid is important here. Selecting depth of cut. Depth of cut is often predetermined by workpiece geometry and operation sequence. In roughing, depth is made as large as possible to maximize the material removal. Also, the horsepower of the machine is a limitation, but our target is to achieve high. Machine tool and setup rigidity and strength of cutting tool is also sometimes affect the depth. In finishing, depth is said to achieve final part dimensions. Determining feed. In general, feed first, speed second. Determining feed rate depends on the tooling. Harder tool material requires lower feed. Roughing or finishing means high feeds. Finishing means low feeds. Constraints on feed in roughing limit imposed by cutting forces, setup rigidity, and sometimes also the horsepower affect the feed. Surface finish requirement in finishing select feed to produce desired finish. Optimizing the cutting speed, select speed to achieve a balance between high metal removal rate and suitably long tool life. Mathematical formulas are available to determine optimal speed. Two alternative objectives in these formulas: maximum production rate and minimum unit cost. Maximum production rate. Maximizing production rate is equal to minimizing cutting time per unit. And turning total production cycles times for one part consists of part handling time (th), machining time (tm), and tool change time per part is (tt) by np, where np is the number of pieces cut in one tool life. So maximum production rate means that total time per unit product for operation that is given by Tc is equal to Th plus Tm and plus Tt by Np. This is the same one factor. Cycle time Tc is a function of cutting speed. Cycle time versus cutting speed. This is time per work part, this is cutting speed, this is Vmax. As you can see, if we move from here, it is low. If we This is for the machining time. Part handling time is constant. Tool change time, if the speed is low, and it moves higher, and total time workpiece. So we will select the speed that is optimum for all of these things. So we will select this Vmax. Minimize cost per unit. This is the second thing. In turning total production cycle, cost for one part consists of cost of part handling time C naught TH, where C naught is the cost rate for operator and machine. Cost of machining time C naught TM, cost of tool change time C naught TT by NP. Tooling cost CT by NP, where CT is cost per cutting edge. So total cost is given by CNC is equal to C naught TH plus C naught TN plus C naught into TT by NP plus CT by NP. Against unit cost is a function of cutting speed, just as TC is a function of velocity. This is the same in previous. Now this is cutting speed and this is cost per work part. So this is optimum, this is tool cost. These are all the graphs we will, this is not by one part, this is a whole big study, and the optimum speed is given, the minimum speed is given this. Comments on machining economics. As C and N increases in Taylor tool life equation, optimum cutting speed should be reduced. Cemented carbides and ceramics tools should be used at speeds significantly higher than for HSS, high speed steel. Vmax is always greater than V minimum. Reason is CT by NP term in cost. Total cost equation pushes optimum speed to left in the plot of CC versus V. As tool change time, TT and or tooling cost CT increases, cutting speed should be reduced. Tools should not be changed too often if either tool cost or tool change time is high. Disposable inserts have an advantage over regrindable tools because tool change time is lower. Product design guidelines in machining. Design parts that need no machining. Use net shape processes such as precision casting, closed die forging, or plastic molding. If not possible, then minimize amount of machining required. Use near net shape process such as impression and die forging. Reason why machining may be required: because close tolerances are required, good surface finishing required, special geometric features such as threads, precision holes, and cylindrical sections with a high degree of roundness is required. Tolerances should be specified to satisfy functional requirements, but process capabilities should also be considered. Very close tolerance add cost but may not add value to the part. As tolerances become tighter, cost generally increases due to additional processing, fixturing, inspection, sortation, and rework and scrap. Surface finish should be specified to meet functional and or aesthetic requirements. However, better surface finish generally increase processing cost but by requiring additional operations such as grinding or lapping. Machined features such as sharp corners, edges, and points should be avoided. They are difficult to machine. Sharp internal corners are required. Pointed cutting tools that tend to break during machining because sharper have more stress concentrations. Sharp corners and edges tend to create burrs and are dangerous to handle. Machine parts should be designed so they can be produced from standard stock sizes. Examples: rotational parts with outside diameter equal to standard bar stock diameter. Product design guidelines in machining. 7. The last, select materials with good machinability. As a rough guide, allowable cutting speed and a production rate correlates with machinability rating of material. Thus, parts made of material with low machinability take longer and cost more to produce. So, we are required to select material with good machinability. Design machine parts with features that can be produced in a minimum number of steps. Examples: design part with geometric features that can be accessed from one side of the part, like this, and this. So we will two parts with similar holes features, holes that must be machined from two sides requiring two steps, and the holes that can all be machined from one sides. So we will require to this. And finally, machined part should be designed with features that can be achieved with standard cutting tools. Avoid unusual hole sizes, threads, and features requiring special form tools. Design parts so that number of individual cutting tools needed is minimized. So I hope you understand the economic and product design consideration for the manufacturing processes. So that's all for the lecture. Sorry for my cough. I hope you didn't mind. See you in the next lecture. Till then, take care. Bye bye.